So this is Math 314, Algebra 1, Lecture 2. And there's a question about one of the homework problems, which is section 1.3, number 2. So let me just share the screen for one moment. And it's the problem about the square card. Consider the symmetries of the square card. Is that the question?
Yes.
Okay. So show that any positive power of R, so R is the rotation by pi over 2 radians around the center. Work out some examples and show this condition is satisfied, and show that R cubed is the same symmetry as rotation by pi over 2 around the centroid, which means the center of the square. So let me stop the share and try to write this down as a problem. So this is problem 1.3.2 on the symmetries of the square. So here is a square, and here is the center, which is the centroid. That's just another name for the center in this case. And let's see what just me go back to the text. So here is this could be a square or a rectangle. But let's say this is the square, and the rotation R is a rotation it should be a rotation around the center by 90 degrees, or by pi over 2 radians. So one rotation would send 1 to this position and 4 over here. If you rotate a second time, the 1 here moves here, and the 4 moves over to here. So, and that's exactly what we see. So this is, when you rotate twice, 1 goes here and then here. So 1 is in this position. 2 goes here and then here, which is what you see, and so forth. So R is the rotation around the center or the centroid by 90 degrees. And A, B, C, and D are reflections. So let me just see where, yeah, I just want to find where how they label them exactly. Yes. So symmetries of the square. So A is a rotation through the center parallel to the sides. B is a rotation through the center parallel to the top and the bottom. C is the rotation through the diagonal from the lower left to the upper right. And D is the rotation through the diagonal from the lower right to the upper left. So those are the 8 symmetries of the square. And you can see here on page 9, they worked out the multiplication table. And what they want you to do in this exercise is, in effect, just check some of the entries in this table. So let me stop the share. Oops, oh, sorry. I guess I never did share. So let me stop the share. and look at the problem. So if we label the corners of the square 1, 2, 3, and 4, and on the paper, we label the positions. This is 1, this is 2, this is 3, and this is 4. So every time we pick up the square, move it in some way, and put this back in its original position, the corners will be exactly where the corners are, but the order in which they're located has changed. So here we have 1, 2, 3, 4. If we rotate it once, 1, 2, 3, 4, the 1 is moved up here and so forth. If we rotate it a second time, so now 1 is here, 2, 3, 4. And the effect of doing it twice, that's r squared. That just means r followed by r. If we rotate it a third time, 1 is down here, 2, 3, 4. And if we rotate it a fourth time, 1, 2, 3, 4. So this is r cubed. And from here to here, that's what we got when we rotated. Try to show this a little bit better. If the paper's not on the screen and you have trouble seeing it, just let me know and I can adjust everything. So r squared, r cubed, this is r to the fourth. And if you look, 1, 2, 3, 4, we're back exactly where we started. So r to the fourth is this real called E, which is the identity motion, the identity symmetry, where you don't change anything. From here to here, everything stays the same. So r to the fourth is the identity. Now, suppose you take this and you apply r again. Well, when you apply r again, you're back here, 1, 2, 3, 4. So r to the fifth is the same as r. And r to the sixth is r squared. And r to the seventh is r cubed. And r to the eighth is r to the fourth, which is E. And r to the ninth is r. And r to the 10th is r times r, is r squared. And what this suggests is that if you take a number k, so k is a positive integer, and you know from elementary school how to divide. If you take k and you divide it by 4, you get a quotient q and a remainder. I'll call the remainder m instead of r, to stick with the notation the book is using. So if any positive integer, in fact, any integer, if you divide it by 4, you have a quotient q and a remainder m, and m is 0, 1, 2, or 3. And if you take r to the k, this is r to the 4q plus m. This is r to the 4q times r to the m. The rules of exponents still hold. And r to the 4q is r to the fourth to the q. And r to the fourth is the identity. So this is the identity to the qth power times r to the m. But the identity symmetry is leave everything the way it is. So if you leave everything the way it is, q times, you haven't changed anything. So this is just r to the m. So this is the statement that you're asked to verify in part A, which is if you take any natural number k, and if you let m be the remainder when you divide by 4, and the remainder is 0, 1, 2, or 3, then r to the k is equal to r to the m. Right? Is there any questions about that? Now, in the second part, it asks about r cubed. So here we can see in the picture what r cubed is. You have the square, you rotate once, twice, 3 times, you end up over here. That's r cubed. And if you look at r cubed and compare it to r, instead of, this is like a rotation backwards by 90 degrees. Instead of rotating one up and everything rotated by 90 degrees in the counterclockwise direction, here you've rotated everything backwards by r. So r cubed is the inverse of the rotation r. The rotation r inverse, you rotate clockwise by 90 degrees or pi over 2 around the centroid. R cubed is equal to r inverse. And one way, because r inverse has the property that if you, the symmetry r inverse reverses the action of the symmetry r. So r inverse times r, or r times r inverse, has to be the identity rotation. And in fact, r cubed has that property because r cubed times r is r to the 4th, which is the identity. So, but part B really is just to look at the picture and to observe that r cubed is the same symmetry, is rotation by pi over 2 clockwise instead of counterclockwise. So r cubed is r inverse. Right. Any questions about that? And the second part of 1.32b is we saw that r cubed is the same as r inverse. So r to the minus k, which means to apply r inverse k times, that's the same as applying r cubed k times, which is r to the 3k, which is equal to r to the m, where (3k), if you divide by 4, is equal to 4 times the quotient plus m. M is 0, 1, 2, or 3, and we could also write it like this because, let's see, so 3k is 4k minus k. And if that's equal to 4q plus m, that's the same as saying that minus k, I'm just taking this and bringing it over to this side, is 4 times q minus k plus m. Let me call this q prime. So minus k, if you divide it by 4, leaves the same remainder of m. So, or in other words, m plus k, let me just leave it like this. So, so this is just rearranging this by, elementary school algebra. M plus k is equal to minus 4 q minus k, or 4 times k minus q. In other words, m is a number between 0, 1, 2, and 3, chosen from 0, 1, 2, or 3, such that m plus k is divisible by 4. this is m plus k is a multiple of 4. So that's what it means to show that r to the minus k is equal to r to the m, and m is the unique integer between 0, 1, 2, and 3, such that m plus k is divisible by 4. Okay. Any questions about that? Any other questions from the homework? Okay. So let's continue. And today we're going to talk about combinations and permutations. So this is, let me just show it on the screen, share screen. So this is on page 16, section 1.5. Permutations. And a permutation is simply the number of ways you can arrange a series of objects or a series of points. So suppose we have 3 objects, and let's just call them the numbers 1, 2, and 3. Right? So what are the different arrays you can arrange these numbers in order? We have 1, 2, 3. We could keep 1 fixed, or actually we could just rotate them. Instead of 1, 2, 3, go 3, 1, 2. Or we could rotate it again and go 1, 2, 3. So here we have the numbers 1, 2, 3 in different orders. Is there any other way we could arrange them? Well, you could keep 1 fixed and change 2 and 3. Or you could keep 2 fixed and change 1 and 3. Or you could keep 3 fixed and change 1 and 2. So we see here are 6 permutations of the numbers 1, 2, 3. You can arrange them in these 6 different orders. Okay. Suppose you only had 2 objects, 1 and 2. There's only 2 ways to write them down in order. You can either write 1, 2 or 2, 1. So in this case, there are just 2 ways to do it. Right? Of course, to make it even easier, if you only had 1 number, there's only 1 way to do it. There's only 1 permutation of 1 object. There are 2 permutations of 2 objects. There's 6 permutations of 3 objects. Right? What is a kind of a standard way to describe a permutation? Let's use these permutations of 1, 2, 3 as an example. We could think of it like this. We have 1, 2, 3, and we could permute it by sending this permutation. We could send 1 to the first 1, 2, 3, two to 1, and 3 to 2. Let's see. So how do I want to think of this? This is just a way of writing a permutation. You can think of it like this. Here we have 1, 2, 3. Think of these as 3 boxes in order, and each containing the numbers 1, 2, and 3. And we want to rearrange these and put 1 number in each box, but not necessarily in this order. So we could put 1 in box 3, 2 in box 1, and 3 in box 2. That's what, so the thing. So here we have our boxes, and we have 1, 2, 3 in order in the boxes. And then we take 1 and we put it in box 3. And we take 2 and we put it in box 1. And we take 3 and put it in box, we take 2 and put it in box 1. We take 3 and put it in box 2. So that corresponds to this arrangement of elements in the boxes. So here we're saying what position you put an element in. You put 1 in box 3, 2 in box 1. Whatever is in box 3, you move into box 2. Okay. So let's try to explore this a little bit more. Suppose we have, so we can think of the way you write a permutation of 3 objects is as in the form of something which looks like this. You have 2 rows of numbers and 3 numbers in each row. So this would be, this is something that's called a matrix. A matrix is just a rectangular array of numbers. In this matrix, we have 2 rows and 3 columns. And in the first row, we put the numbers 1, 2, 3 in order. And in the second row, we can put the numbers 1, 2, 3 in any order. And how many different orders are there? Well, we just saw there's 6 orders. There's no other permutation of 3 objects there. Every permutation of 3 objects is one of these 6. And we're going to think of a permutation as a kind of function, just like you had in calculus. This is a function that sends 1 to 2, 2 to 3, and 3 to 1. Or it takes the object in box 1 and puts it in box 2, and the object in box 2 puts it in box 3, and so forth. Right. Right. So this is going to be the standard notation we use for permutations. And we can consider this as a function, just like in calculus. You know, in calculus, we had a function y equals f of x. Let me call this function, I'll give it a, this is the Greek letter sigma. So I'm going to call this sigma. And so in this case, if sigma is 1, 2, 3, 2, 3, 1, this is the function such that sigma of 1 equals 2, sigma of 2 equals 3, sigma of 3 equals 1. Suppose I have another permutation, which I'll call tau. You like Greek letters in mathematics, tau. Suppose tau is the permutation 1, 2, 3, 3, 2, 1. So tau is a function which sends tau of 1 to 3, tau of 2 is equal to 2, and tau of 3 is equal to 1. And in calculus, everyone's taken calculus, you look at composition of functions. So we could look at the composition, sigma tau. This is multiplication of permutations or composition. Same thing, in other words, just 2 words for the same thing. Composition or multiplication of permutations. What is sigma tau? So it's the composition of these 2 functions. Is there a question? So sigma was 1, 2, 3, 2, 3, 1, and tau was 1, 2, 3, 3, 2, 1. So we think of this as composition of functions. This is a function from 1, 2, 3 to 1, 2, 3 in some order. So what is sigma tau of 1? So you remember how you define composition of functions in calculus and in pre-calculus. This means sigma of tau of 1. Tau of 1 is 3, so this is sigma of 3. What is sigma of 3? It's 1. So sigma tau sends 1 to 1. What is sigma tau of 2? That's sigma of tau of 2. Tau of 2 is 2.
Professor, can you move up a little bit? Yeah, thank you.
So that's sigma of 2. Sigma of 2 is 3. So sigma tau sends 2 to 3. What is sigma tau of 3? That's sigma of tau of 3. Tau of 3 is 1. So that's sigma of 1. Sigma of 1 is 2. So sigma tau of 3 is 2. So sigma tau is this permutation. 1, 2, 3 goes to 1, 3, 2.
Professor, can you explain this again, please? Sorry.
So remember in calculus, you might have something like f of x is equal to the sine of x. And g of x might be e to the x, right? And you have the composite function, f composed with g of x. That means f of g of x. This means f of e to the x, which is the sine of e to the x, right? So this was composition of functions in calculus. Okay? And
yes,
it's the same notion of composition of functions. So sigma is a function that sends the numbers 1, 2, 3 to the numbers 1, 2, 3. And tau is a function that sends the numbers 1, 2, 3 to the numbers 1, 2, 3. And I want to consider what is the composite function sigma tau. So sigma tau is going to be another function that sends 1, 2, 3 to 1, 2, 3, but we need to compute it. So sigma tau of 1, this is composition. This means sigma of tau of 1. This is tau. Tau sends 1 to 3. Tau of 1 is 3. So sigma of tau of 1 is sigma of 3. This is sigma. Sigma of 3 is 1. So sigma tau of 1 is equal to 1. So the composite function, or the product of these two permutations, sends 1 to 1. Let's do it in the opposite order. Let's compute. Now, notice for functions in calculus, this is f composed with g. What is g composed with f? That's g of f of x. G is, so this is g of sine of x. G is the exponential function. This is e to the sine of x. And you notice f composed with g is different from g composed with f. So you're very familiar with that from calculus. And in algebra, the same thing can happen. Let's look at tau sigma. Let's compute tau sigma. So tau sigma of 1, that means tau of sigma of 1, sigma of, this is sigma, and this is tau. Well, actually, so sigma of 1 is 2, so this is tau of 2. And tau of 2 is 2, so tau sigma of 1 is equal to 2. If I make my little table over here, what is the permutation tau sigma? 1, 2, 3. Well, 1 goes to 2. What is tau sigma of 2? Tau sigma of 2 is tau of sigma of 2. Sigma of 2 is 3. So this is tau of 3. Tau of 3 is 1. So tau sigma of 2 is 1. 2 goes to 1. What is tau sigma of 3? Tau sigma of 3 is tau of sigma of 3. Sigma of 3 is 1. So this is tau of 1. Tau of 1 is 3. So tau sigma of 3 is 3. So 3 gets sent to 3. And you notice sigma tau is the permutation that sends 1, 2, 3 to 1, 3, 2. Tau sigma is the permutation that sends 1, 2, 3 to 2, 1, 3. These are different. So sigma tau is different from tau sigma. So this is a very important fact about permutations. You can, when you multiply permutations, the order matters. It's not like multiplying numbers. 3 times 5 is 5 times 3. The order doesn't matter. But for permutations, just as with functions, multiplication of permutations is not, as we say, commutative. Sigma tau, I mean, it may be equal to tau sigma, but in general, it's not. So you can't assume that it is. So the whole object of the first semester of algebra is to understand what are called groups. And we will see very soon that a fundamental example of what is a group comes from permutations. So permutations are very, very, very important. Let's say a little bit more about our notation for writing permutations. So a permutation of n objects and we'll usually just take the numbers 1 up to n as the objects, is a function. Basically, it's a function from the set to itself. So we would write it as, we write the numbers from 1 to n in the first row of a matrix, and the second row of the matrix is where each number gets mapped to. So suppose we had the permutation 3, 2, 1. This is a permutation of 7 objects. 3, 2, 1, 7, 4, 5, 6. So this means you have the numbers 1 through 7. Oops. Sorry, just 1 second, please. So this is a permutation of 7 objects, 1 through 7, or of the numbers 1 through 7. 1 goes to 3, 5 goes to 4, and so forth. So this is a permutation. And you can multiply permutations so long as the permutations on the same number of objects. So suppose we have another permutation, 1, 2, 3, 4, 5, 6, 7, and this gets sent to 4, 3, 1, 2, 6, 5, 7. So I have this permutation and this permutation. And what is the product? It's the composite of these two functions. Each of these permutations is a function of the integers from 1 to 7 to the integers from 1 to 7. And I want to calculate, so this is a basic calculation in algebra. You will have to do this many, many times, and it'll certainly be on every exam you take in algebra to do a computation of this sort, explicitly or implicitly. What is the product of these two symmetries or these two permutations? So this is composition of functions. It's this function followed by this. And you can trace it out as follows. If you look.
7.
Yes. Question?
Oh, no, I said the answer is 7.
All right. So, yes, that is true. So if you look at this, 1 goes to 4, and 4 goes to 7. So 1 goes to 7. 2 on the right goes to 3, and then 3 gets sent to 1. So 2 ends up at 1. 3 goes to 1, and 1 goes back to 3. So 3 doesn't move. 3 stays at 3. 4 goes to 2, and then 2 stays at 2, so 4 ends up at 2. 5, the permutation on the right sends 5 to 6, and the permutation on the left sends 6 back to 5. So 5 stays at 5. Let's see. 6 gets sent to 5, and 5 here gets sent to 4. So 6 goes to 4. And 7 goes to 7, and then 7 goes to 6. So 7 ends up at 6. So we have that the product of these two permutations is a third permutation, 7, 1, 3, 2, 5, 4, 6. A very important permutation is the identity permutation, E. And the identity permutation sends every number to itself. So if the second row is the same as the first row, that's always the identity permutation. And for every permutation sigma, E times sigma or sigma times E is just sigma because E leaves everything exactly where it is. If sigma sends 3 to 5, E sends 5 to 5, so 3 ends up at 5 and so forth. Now, permutations have some important properties. So you remember from calculus, even I hope from pre-calculus, composition of functions is associative. That means if you have functions f, g, and h, f composed with g composed with h is the same as f composed with g composed with h. Composition of functions is a binary operation. You compose things two at a time. So f composed with g composed with h is the same as f composed with g composed with h. This is the associative rule for anything. And you'll notice it's very important. The order, the sequence f, g, and h is the same on both sides. We didn't change the order. We changed the bracketing, the parentheses. And exactly the same is true for permutations. Because a permutation is just a function. So if you have permutations rho, sigma, and tau, rho times sigma times tau is the same as rho times sigma tau. The associative law for permutations follows from the fact that you have the associative law for a composition of any kind of functions. But it's also true, see, for some functions, suppose you have the function f of x equals, I don't know, x cubed. So the graph looks like that. And you have another function, g of x, which is the cube root of x. That looks like that. And if you take f composed with g of x, that's f of g of x, that's f of the cube root of x, that's the cube root of x cubed, that's just x. And g composed with f of x is g of f of x, that's g of x cubed, that's the cube root of x cubed, that's also x. So this is just the identity, e of x. Right? E of x is just, f of x equals x, or e of x equals x. So some functions have what you might call an inverse, because we have fg and gf are both equal to e. So we would say that g is f inverse. If you take f followed by g, you come back to where you started always. Not every function in calculus has an inverse, but every permutation is a function that has an inverse. So I want to let sigma inverse be that's what this is, this is how you read this. Sigma inverse. So this is going to reverse the action of your permutation. So suppose we have sigma is equal to here's a permutation of numbers 1, 2, 3, and 4. So what does sigma do? Sigma sends 1 to 3, 2 to 2, 3 to 4, and 4 to 1. I want sigma inverse to reverse the action of sigma. So if sigma sends 4 to 1, the inverse will send 1 back to 4. If sigma sends 2 to 2, the inverse sends 2 back to 2. If sigma sends 1 to 3, the inverse sends 3 back to 1. And if the sigma sends 3 to 4, the inverse sends 4 back to 3. So we would say that sigma inverse is the permutation where 1 goes to 4, 2 goes to 2, 3 goes to 1, and 4 goes to 3. That's how we calculate sigma inverse. And if we actually compute sigma composed with sigma inverse, what is that? 1 goes to 4, and 4 goes back to 1. 2 goes to 2, and 2 goes to 2. 3 goes to 1, and 1 goes to 3. 4 goes to 3, and 3 goes to 4. So this is just the identity, right? Sigma inverse is the identity. And if you do the same calculation for sigma inverse times sigma, you'll see you also get the identity. Right. Any questions about this? So it's nice to give a name for these things we're talking about. So we let Sn be the set of permutations of the integers from 1 to n.
I'm sorry. Can you go back to the last page real quick?
Yes.
Okay, thank you. I just wanted to see the last part again.
Right.
The sigma inverse. Thank you.
Right. So the Sn be the set of all of these permutations. And well, what are some things we can say about this? First of all, it's closed under multiplication. Because the product of two permutations is another permutation. This multiplication, which is just composition of functions, is associative. There is always the identity permutation. And every permutation sigma has an inverse. There's another permutation we call sigma inverse, such that when you compose the two of them, sigma inverse and sigma inverse sigma are both equal to the identity. So this set of permutations satisfies these algebraic properties. It's closed under multiplication. The multiplication of two permutations is associative. There's always an identity permutation, and every permutation has an inverse. And we'll see these are the properties of what in algebra is called a group. So a very important example of a group in algebra is the group of all the permutations of the set of the first n integers for every n. And that really is something to keep in mind. Now, some permutations have a very pretty property. For example, suppose we take n equal to 7 and consider the permutation sigma, which is
You can have 5, 2 times, right?
yeah, no, I know. I'm trying to do this. Make that a 1. Okay. So here's a permutation, and this is in S7. So this symbol, which is a Greek epsilon, means in. So in the language of mathematics, S7, I just defined that. That's the set of all permutations of the numbers 1 through 7. This is a permutation of the numbers 1 through 7. So this is one element of the set S7, and that's what this says. This permutation is in this set. So 1 goes to 5, 2 goes to 1, 3 goes to 3, 4 goes to 4, 5 goes to 7, 6. So we could ask what happens. Suppose we start with the number 1. Where does 1 move under sigma? So 1 goes to 5. Where does 5 go? 5 goes to 7. 7 goes to 2. 2 goes back to 1. 3 doesn't go anywhere. It goes to itself. And 4 just goes to itself. And 6 just goes to itself. So what this permutation does, you kind of have this sort of cycle. 1 goes to 5, 5 goes to 7, 7 goes to 2, 2 goes back to 1. Yeah. And a permutation like this is called a cycle. And this particular cycle has 4 numbers in it. This is a cycle of length 4. Actually, let me change this permutation a little bit. So in this permutation, 1 goes to 5, 5 goes to 7, 7 goes to 2, 2 goes back to 1. What about the other numbers? 3, well, 3 goes to 6, 6 goes to 4, and 4 goes back to 3. So this is also a kind of a cycle. This is a cycle of length 3. And there's a kind of a special notation for a cycle. So this cycle, 1 goes to 5, goes to 7, goes to 2, goes back to 1. So that's just that this is the permutation that sends 1 to 5, 5 to 7, 7 to 2, 2 back to 1. Of course, there's nothing special about 1. I could look at this cycle and say, well, also 5 goes to 7, goes to 2, goes back to 1. It's the same permutation. Or I can start with 7 and look at this cycle. 7 goes to 2, goes to 1, goes to 5. Or I could have started with 5. So here I started with 1, 5, 7. I could start with 2. So 2 goes to 1, goes to 5, goes to 7. So here I have 4 cycles. And they look different because the numbers are in different orders, but they represent exactly the same permutation. All of these send 1 to 5, 5 to 7, 7 to 2, 2 to 1, 1 to 5, and so forth forever. This cycle I could write as 3, 6, 4. 3 goes to 6, 6 goes to 4, and so forth. And in fact, and this is very important, every permutation decomposes into a product of cycles. You can write every permutation as a product of cycles. This is like, in some sense, if you have the positive integers, like you have the number 120, you can write this as a product of primes, because 120 is, what is it? It's 8 times 3 times 15. I believe that is correct. Is that right? 60? No. 40. That's not right. 8 times 3 times 5. And 8 is 2 times 2 times 2 times 3 times 5. So here I have the number 120, and as I wrote it as a product of prime numbers, 2, 3s, and 5s. So that's a decomposition of a positive integer into a product of primes. And very similar to that, you can take a permutation and decompose it into a product of cycles. So let's look at another example. Suppose I take the permutation, I'll call it pi. 1, 2, 3, 4, 5, 6, 7. 4, 3, 1, 2, 6, 5, 7. So if I look at this permutation, let me just start with 1 and follow it around. 1 goes to 4, 4 goes to 2, 2 goes to 3, and 3 goes back to 1. So this is like a cycle, 1, 4, 2, 3. See, 5 goes to 6, and 6 goes back to 5. So that's like the cycle 5, 6. And 7 goes to 7. So I could write this permutation as the product of the cycles 1, 4, 2, 3, 5, 6, and 7. And in this decomposition into a product of cycles, you'll notice several things. First, the numbers in each cycle are different. These are what we call disjoint cycles. Here we have 1, 2, 3, 4. Here we have 5, 6. Here we have 7. You don't have the same number occurring twice. Second, these disjoint cycles, so it's called these disjoint, that means they have no element in common. These disjoint cycles can be permuted. This is the same as the cycle 5, 6, 1, 4, 2, 3. And I don't even have to write down the cycle of length 1. I can, but it just means it doesn't move anywhere. So this is what is called the cyclic decomposition of a permutation. It's a product of these disjoint cycles. So this is cycle notation. So just to emphasize this, here you see the text, and they're describing cycle notation. So two cycles are disjoint. If each leaves fixed, the numbers move by the other. So for example, 1, 4, 2, 3, 5, 6, this is a product of disjoint cycles. The numbers here are different from the numbers here. And as an example, at this point, the book is calculating. If I take the permutation 1, 3, 4, 7, 6, 5, that's one permutation, and 1, 4, 2, 3, 5, 6, that's another permutation. I want to multiply these two together. So let's stop the share. So here I wrote down those two permutations. This is one permutation, and this is another permutation. These are two disjoint cycles that make up one permutation. These are two disjoint cycles that make up a second permutation. So let's calculate what this is. Let me first write this in the standard form. 1, 2, 3. These are both permutations of the numbers 1 through 7. So this permutation sends 1 to 4, and this sends 4 to 7. So 1 ends up at 7. This permutation sends 2 to 3, and this sends 3 to 1. This sends 3 to 1 and 1 to 3, so 3 stays at 3. This sends 4 to 2, and you don't see a 2 here. That just means 2 stays at 2, so 4 goes to 2. This sends 5 to 6, and this sends 6 back to 5. This sends 6 to 5, and this sends 5 to 4. This doesn't, you don't see a 7 here. That means 7 just stays at 7, and this sends 7 to 6. So the product of these two permutations is this permutation. And if I want to write this as a cycle, what is this? 1 goes to 7, 7 goes to 6, 6 goes to 4, 4 goes to 2, 2 goes back to 1. And what numbers don't occur here? 3 goes to 3, and 5 goes to 5, so I don't need to write them. So the product of these two permutations written using cyclic notation is this permutation in cyclic notation. This just turns out to be one cycle. Right? So while we are at this, let me introduce a little bit more important concepts. The order of a permutation sigma is the smallest positive integer k such that sigma to the k is the identity. And a cycle of length k has order k. This is really a little theorem. Suppose we had a cycle A1, A2, A3, up to A sub k. So this means A1 goes to A2, goes to A3, goes to A4, and so forth, goes to A sub k minus 2, A sub k minus 1, A sub k, and A sub k goes back to A1. So that's kind of a picture of a cycle of length k. So when do you get the identity? The identity, sigma to the k equal to the identity, means sigma to the k of ai, any one of these numbers, is the same ai. So how many times do I have to iterate the permutation for a1 to come back to itself? If I do sigma once, a1 goes to a2, then to a3, then to a4. If I do apply sigma 3 times, 1, 2, 3, I end up at a4. If I do it k minus 1 times, I end up at ak. If I do it one more time, ak goes to a1. So a cycle of length k has order k. You can really just see that from the picture. Let's see, suppose I have the permutation the cycle 1, 2, 3. So if I apply that once, 1 goes to 3. Sorry, 1. So 1, 2, 3. So if I apply that once, I'm happy to write that. So 1, 2, 3. This is, if I write this in the standard form, 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is my sigma. This is cyclic notation, cycle notation. This is what I call these matrices with two rows, what I call standard notation. This has order 3. Suppose sigma is the permutation, which is 1, 2, 3, and 4, 5. So what does this mean? If I were to write this in standard form, 1 goes to 2, 2 goes to 3, 3 goes back to 1, 4 goes to 5, 5 goes to 4. That's this permutation. And what is the order of sigma? Well, I claim the order of sigma is 6. Why is that? Well, if I apply sigma 3 times, 1, 2, 3 gives me the identity, but 4 goes to 5, goes to 4, goes to 5. So sigma cubed is 1, 2, 3 cubed, 4, 5 cubed. 1, 2, 3, that applied 3 times, that's just the identity. And 4, 5, has order 2, so if I apply it 3 times, this is just 4, 5. This is just 4, 5. And so sigma to the 6th, which is sigma cubed squared, is the permutation 4, 5 squared. That's the identity. And you can check that nothing smaller that will work. Yeah, maybe that's all I'm going to say today about permutations, because I'm going to spend Wednesday also talking about permutations. But what you should do is spend a lot of time studying section 1.5 on permutations, because everything in this section is important and you have to know. We will use it constantly throughout the semester. And you might look at section 1.5. Homework problems for next week are from this section. And you might look at some of them, and I'm happy to answer questions about them if you have any next on Wednesday. But really spend a lot of time studying permutations, making up small examples yourself. I mean, here's a typical kind of problem that you should know. Suppose you have a permutation, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to write down a permutation of 1 through 12. I'll just make up numbers: 7, 6, 12, 3, 1, 11, 8, 2. What haven't I used yet? 4, 9. So I have 1, 2, 3, 4. I need a 5, 6, 7, 8, 9, 10. Okay. So here is a permutation. I'm just drawing those vertical lines so I can see what goes with what. Here's a permutation of the numbers 1 through 12. I want to write it as a product of cycles. So let's see. I can start with 1. 1 goes to 7. 7 goes to 8. I have no idea what's going to happen. 8 goes to 2. 2 goes to 6. 6 goes to 11. 11 goes to 5, and 5 goes back to 1. So this permutation includes this cycle 1, 2, 3, 4, 5, 6. This is a 7 cycle, a cycle of length 7. See, what haven't I used yet here? I haven't used 3. So 3 goes to 12. 12 goes to 10. 10 goes to 9. 9 goes to 4. And 4 goes back to 3. So that's a 5 cycle. So this permutation, this is in S12. It's a permutation on the numbers 1 through 12. This permutation is a product of two disjoint cycles, a 7 cycle and a 5 cycle. All right. Well, that's kind of interesting. And that's a typical kind of problem that you have to be able to use. Okay. Any questions about this? All right, so now we're really getting into some algebra. That's really good. Permutations are very, very, very important. So study this, and I will see you on Wednesday. Okay. And the video will be on YouTube shortly. Bye, all.
Bye. Professor,
Yes,
you said to study section 1.5.
yes. The
Okay.
section on permutations.
All right, thank you.
Okay.
And how are you doing attendance?
I just look at the list of participants. When you log on, your name pops up.
Okay. All right, thank you.
All right, bye.